let's look at some trinomial factoring. Trinomial factoring hinges upon the following. If we take the product of two binomials, x plus a times x plus b, the result will be x squared plus a plus b times x. Do you see that? Because that's ax and bx you get from the cross terms. That's a plus b times x plus ab. And of course, a and b could be positive or negative. But the idea is that if you multiply two binomials together, you get a trinomial with an x squared, a middle term, something times x, and a constant term at the end. Now notice, this formula is only right if the binomials are of the form x plus a and x plus b. If there's any coefficient on the x, then we're going to have a different formula. But we'll worry about that a little later. Right now, we're going to look at some simple problems, starting with number 1. We have x squared plus 8x plus 15. Now think about what that formula said. We're looking for factors of the form x plus a times x plus b. Let me just write that down. X plus a times x plus b is what we're looking for, where these two numbers a and b have to be chosen so that a times b is this number 15 and a plus b is this number 8. Now let's see what kind of information we have. A times b is plus 15. That means either a and b are both positive or a and b are both negative. But is that right? Because to get a positive result, we have to multiply either two positives or two negatives. But in addition, we have a plus b has to be 8. Now, if a plus b is plus 8, and our choice is that they're either both positive or both negative, then clearly they both have to be positive. So we're looking for two positive numbers, a and b, which have the property that a times b is 15 and a plus b is 8. So let's look at the factors of 15, the whole number factors of 15. And the only possibilities are 1 and 15, because 1 times 15 is 15, and 3 and 5, because 3 times 5 is 15. And now we ask, for which of these two cases is the sum of the two factors equal to 8? And of course, that's easy. 1 and 15 is 16, so it can't be that. But 3 and 5 add up to 8. Result is, we conclude that the proper factorization for this is x plus 3 times x plus 5. Well, of course, you might have written it x plus 5 times x plus 3, but that's the same thing because those are the same two factors, and it doesn't matter which you write first or which you write second. Now, let's just check that this really is correct. If we multiply this out, this is x times x is x squared. X times 5 is 5x. Now we go to the second term. 3 times x is 3x. 3 times 5 is 15. And you have x squared plus 5x plus 3x adds up to 8x. So you have x squared plus 8x plus 15. And this thing really checks. All right, the only way to really factor trinomials is by trial and error, find the proper factors, and then check your answer by multiplication. Always check your answer. It's very, very easy to fall into a trap and factor these things incorrectly. In number 2, we have x squared minus 10x plus 21, and we want to factor this. Once again, remember the rule. We want to find two factors of the form x plus a times x plus b. We need two numbers a and b such that the product of a and b is 21 and the sum of a and b is minus 10 this time. Now remember, the product of a and b is plus 21. Again, if the product is plus, either they're both plus or they're both minus. The sum is minus 10. Well, clearly, again, if they're either both plus or both minus and they add up to minus 10, then they've got to both be minus. So we want to look at two factors whose product is 21 and whose sum is 10, and we're really going to make them both minus. And what are the factors of 21? Well, again, the factors of 21 are 1 and 21 and 3 and 7. Okay? That's the only possibilities. And 1 and 21 won't work because 1 plus 21 adds up to 22. But 3 and 7 will work because 3 plus 7 adds up to 10. But remember, I don't really want 10. I want minus 10. So my factors that I want to work with are not x plus 3 and x plus 7, but x minus 3 times x minus 7. And let's check that out. This is x squared. All right, can I do this in my head? Well, maybe this time I'll write it down for you. This is x squared, all right, minus 7x, minus 3x, and minus 3 times minus 7 is plus 21. And we have x squared minus 10x plus 21. And the factorization checks once again. If we go on to example 3, we have x squared minus 10x plus 25 to be factored. All right? Once again, we look for factors of 25 whose sum is minus 10. Once again, this is plus. The middle term is minus. That means we need two negative numbers. And what are the factors of 25? Well, the factors of 25 are either 1 and 25 or 5 and 5. And it's easy to see that the thing that's going to work is 5 and 5, because 5 plus 5 is 10. Again, we don't really want 5 plus 5. We don't really want 5 and 5. We want minus 5 and minus 5. So the factorization that we have here is equal to x minus 5 times x minus 5. That's a strange one. The two factors are actually the same. And of course, sometimes you're going to find this written in books as x minus 5, the quantity squared, because x minus 5 times x minus 5 is, of course, x minus 5 squared. Once again, check it now in your head. This is x squared minus 5x minus another 5x is minus 10x, and minus 5 times minus 5 is plus 25, and we know we're correct. Number 4, we want to factor y squared minus 2y minus 8. And of course, what we want to look for are two binomial factors, one which would be y plus a and the other y plus b. But remember, even though it says y plus a and y plus b, a and b could each be, or either be, a negative number. So that even though it says plus, we really could be writing something like y minus 5 or y minus 12 or something like that. All right? And in this case, that really is going to be a serious problem because remember, we want the product of a and b to be this third term. And the third term is minus 8. That means we want two numbers whose product is minus 8. And of course, the sum of those two numbers has to be minus 2. Now let's think. The product of two numbers has to be minus 8. That means one of them has to be positive and one of them has to be negative. All right, what are the possibilities to get a product of minus 8? Well, you could have 1 times minus 8. You also could have minus 1 times 8. Or you could have, what else for minus 8? Well, you could have 2 times minus 4. Or you could have minus 2 times plus 4. Is there any other possibility? I don't think so. I think we've got them all. And now, remember what the other condition is. The other condition is that when you add these two numbers, they have to add up to minus 2. Well, let's see. If I take 1 plus minus 8, that's going to be minus 7, so that can't be right. Minus 1 plus 8 adds up to plus 7. That's not right. 2 plus minus 4 is minus 2. That's the one I want. Notice this last one, minus 2 plus 4, would have given me plus 2. Would have been close, but not quite right. Wrong sign. So this is the one I want, and therefore my factors are y plus 2 and y actually plus minus 4, or simply y minus 4. And let's check that one in our heads. Y squared first, minus 4y plus 2y is minus 2y. That's what we wanted. And the last term is plus 2 times minus 4, which is minus 8. In problem 5, we have x squared plus x minus 6. Once again, we have a final term here that is negative. So we want to find two numbers whose product is minus 6. That means it's going to be one positive number and one negative number. The sum is going to have to be what? The coefficient of x. The coefficient of x is 1. So don't forget, I want two numbers now whose product is minus 6 and whose sum is plus 1. All right? Let me see. What are the possible factors of minus 6? Well, I could have 1 and minus 6, or I could have minus 1 and plus 6. Or I could have 2 and minus 3, or I could have minus 2 and plus 3. Are there any others? Well, let's see. I could have 3 and minus 2, but that's really the same as minus 2 and 3. So I think we've got them all. And we're going to take a look at these and see which pair has the property that when you take the sum of the two numbers, you get this number over here, which, remember, we understand to be 1. So let's see. 1 plus minus 6, that can't be right. Minus 1 plus plus 6, no, that's 5. That's wrong. 2 plus minus 3, no, that's minus 1. That's no good. Minus 2 plus 3, that's right. Minus 2 plus 3 is 1. So this last pair that we picked out is the pair we really want. And the factorization here is x minus 2 times x plus 3. Once again, I could just as easily have written it as x plus 3 times x minus 2. It doesn't matter which order you write the factors. Let's check it. X squared plus 3x minus 2x is plus x. Minus 2 times plus 3 is minus 6 for the last term. Now, after a while, you're really going to begin to learn that when you have ones like this, if you see that you have a product of two numbers that's negative and the sum is positive, then in fact you know that one of your factors has got to be a positive, one has to be a negative, and the positive number's got to be the one that's bigger so that the cross term turns out to be plus. Did I say that right? In other words, here the positive number is a plus 3, the negative number is a minus 2, so in absolute value 3 is bigger than minus 2, and that's why this sum turns out to be plus. Maybe you'll get a shortcut after a while. For now, try to look at all those factors and make sure you don't overlook any. In problem 6, we have a squared minus 13a minus 48. Now here we're going to have to look for two numbers whose product is minus 48 and whose sum is minus 13. 48 has a lot of factors. And if you really start writing them all down, you get things like this. 1 and 48. Sorry, I guess it's got to be minus, so it's 1 and minus 48. Well, that's not going to be right. Minus 1 and plus 48. What other possibilities are there? Well, you can factor a 2, so you can get 2 and minus 24. You can get minus 2 and plus 24. Now, I'm really checking these in my head as I'm going along, and I can see that these aren't going to work either. Then I can get, what? 3 and minus 16, or minus 3 and plus 16. And whoa, I think this one's going to work, isn't it? 3 plus minus 16 is minus 13. Now, I could go on. I mean, after all, I can factor a 4 here. I could factor a 6. So there's really two more sets that I could look at, and I've got to look at plus and minus. But it's going to take a long time. And since as I've come along here, moving through systematically, I found the right answer, I'm not going to check all the other pairs. There's only one pair that's going to work. And this one is going to be it. So the ones I want are 3 and minus 16, which means my factorization here is a plus 3 times a minus 16. By the way, that's an easy one to overlook. People look at it and think, oh, 48 is 6 times 8, and don't go any further and think they can't do the problem. But in this one, the right factorization is a plus 3 times a minus 16. Let me check that. A squared minus 16a plus 3a, that's minus 13a, minus 48. Now, I don't want to leave you with the impression that every trinomial can really be factored. In fact, if I had taken this same problem but it was changed by one number. Let's say it was a squared minus 13a minus 49, and I wanted to factor it. Well, the only possible factors of 49, you see, are 1 and 49, or actually in this case 1 and minus 49, or minus 1 and plus 49. And the only other possibility is plus and minus 7, right? 49, the only other factors are 7 and 7. So I have minus 7 plus 7. Well, this is going to add up to minus 48. This is going to add up to plus 48. This is going to add up to 0. So this thing could not be factored the way we've been factoring. And in fact, most trinomials really can't be factored. If you wrote down an arbitrary trinomial, the chances are pretty good you're not going to be able to factor it. But the ones we've done can be, and the only way to know for now is simply to check every possible pair of factors and find the one that works. If there isn't one that works, then it can't factor. Number 7, factor 2y squared plus 5y plus 2. Now, this is just a little more difficult than the ones we've been doing because we're not starting with just y squared, we're starting with 2y squared. That means that we expect to find factors not y plus a times y plus b, but at least one of the factors has to have a coefficient on the y. In particular, what I expect to find as factors is something like this: 2y as the start of one of them, and y as the start of the other. So the 2y times y will give me that 2y squared term to start. All right? Now, fortunately, this one has some saving features. The last term is plus 2. Now, we know that the two numbers I'm going to put here and here have to be factors of 2. And fortunately, the only factors of 2 are 1 and 2. Also, since it's plus, I know that I've got to have either 2 positive or 2 negative. And I can't possibly have 2 negative because the middle term is going to come out plus. In other words, in this particular case, I know that I have 2y plus something and y plus something. And my choice is to make this 2y plus 2 and y plus 1, or the other way around. The order is really going to make a difference because one of these factors starts out 2y. The other factor only starts out y. Let me say that again. The only factors of 2 are 1 and 2. So let me try it. I can put a 2 in here and a 1 in here. 2 times 1 is 2. And then I check my middle term. This is the only way. I must check the middle term. All right? The middle term, remember, is what I get when I do this times this. That's 2y times 1, which is 2y. And then I have to add to what I get from this product. That's another 2 times y, which is 2y. And I check, and lo and behold, these add up. 2y plus 2y is 4y. Well, 4y is not the same as 5y. So this is wrong, meaning that I must have this, 2y plus something and y plus something. Now remember, I tried a 2 and a 1. And the only other possibility is a 1 here and a 2 here. Now let's see if this one checks. If this doesn't check, then I can't factor this trinomial. Well, let's see. The 2y squared, of course, checks. We know that. And the last term, 2, checks. That's where we got the numbers from. So let's just check that cross term. 2y times 2 is 4y. And 1 times y is y. 4y plus y is 5y. And that one checks. So the proper factorization is 2y plus 1 times y plus 2. All right? This one was easy enough because we didn't have many facts to look at. But you can see that if you have a problem where you start out with something other than just y squared or x squared, whatever it is, if this coefficient is anything other than 1, you're going to have to do a lot of checking. You're going to have to look at all the possible factors. You're also going to have to be careful about the signs. In number 8, you're asked to factor 3a squared minus 10a plus 8. Once again, I realize that the two factors here have got to start out as one 3a and the other a. All right? I've got to take factors of 3 as the coefficients of a, and the only possible factors are 3 and 1. So I have 3a and a. Now, what about out back here? I have to get a plus 8. Either I've got to have two positive factors or two negative factors. They can't be positive because the middle term is going to be negative. So I've got to be looking for two negative numbers whose product is 8. And what are the possibilities? Well, I could be looking at minus 1 and minus 8. I could be looking at minus 2 and minus 4. Now, those are the only possibilities, but you see, I can put those in different positions. I could make this one, say, minus 1 and this minus 8. That's one possibility. And let's check and see if that one works. All right? This is cross term only I have to check. This is minus 24a minus 1a is minus 25a. That's not right. All right, that one's not correct. Now, does that mean I can eliminate the possibility minus 1 minus 8? Not quite, because there's also this possibility. There's the possibility that I have the 8 here and the 1 here. All right, so let's check this one. The cross term is minus 3a minus 8a. That's minus 11a. Close, but not quite. I need minus 10a. Now I've tried the minus 1 minus 8 in both possible places, so I can eliminate that. And we'll try the other possibility, which is minus 2 and minus 4. All right? First, I'll try the minus 2 here and the minus 4 here, and let's check the cross term. Okay? I have minus 12a minus 2a is minus 14a. Well, that can't be right. So let's try the only other possibility, which is a minus 4 here and a minus 2 here. And now we'll check this one. 3a times minus 2 is minus 6a. Minus 4 times a is minus 4a. Wait a second, I think we're right. Minus 6a plus minus 4a adds up to minus 10a, and that's the one we want. Now let me rewrite it just a little more neatly, because now we know what the result is. This is 3a minus 4 times a minus 2. Number 9, factor 5x squared minus 3x minus 8. Once again, we have a trinomial where the leading coefficient is not 1. So we expect to find factors that look something like this. 5x in one factor and x in the other. Now, what about the constant terms in these two factors? Well, their product has to be minus 8. So one of them has to be negative and one has to be positive. And let's see what the possibilities are. The factors of minus 8 would be 1 and minus 8, or minus 1 and plus 8. The other possibility is 2 and minus 4, or minus 2 and plus 4. All right? But of course, you've got to realize that these things not only the possible factors, but they could go in here and here, or they could be reversed. So let's start with 1 and minus 8, and we'll try putting the plus 1 here and the minus 8 here. And we'll check that cross term. Remember, the first term and the last term are taken care of because we picked the numbers to make those work. So let's just try that cross term. 5x times minus 8 is minus 40x. 1 times x is x. Minus 40x plus x is minus 39x. That's certainly not minus 3x. So that pair is clearly wrong. Now, does that mean we're through with that pair? No, we're not through with that pair. We could put the minus 8 over here and the plus 1 over here. And now we check once again. the cross term, we get 5x times 1 is 5x, and minus 8 times x is minus 8x. What did I say? 5x plus minus 8x. That sounds right to me. 5x minus 8x is minus 3x. So that's the right one. And our factorization is definitely 5x minus 8 times x plus 1. Problem 10. Factor 6x squared minus 5x minus 4. Now this problem is going to take quite a bit of checking because here we have as a leading coefficient 6. And 6 can be factored in two ways. It can be 6 times 1 or it can be 3 times 2. So we're going to have to look at two possibilities. We're going to have to look at factors of this form where the lead terms in the binomials are 6x and x, and we're also going to have to look at the possibility of 3x and 2x. Now, for each of these cases, we're going to have to check all the possible pairs of factors of minus 4. Is that right? That means we've got to look at 1 and minus 4, minus 1 and plus 4, and 2 and minus 2. Of course, the other possibility would be minus 2 and plus 2, but that's the same as 2 and minus 2 because we really are going to try every possible arrangement that we can put into these parentheses. So let's start right out with 1 and minus 4. So we'll try plus 1 here and minus 4 here. And we're going to have to check the middle term, and we're going to try to do this quickly in our heads. This is minus 24x here, plus x is minus 23x. That's not right. So let's change that. Now, how do we change it? Well, we'll put the minus 4 over here and the plus 1 over here. And check again. We have 6x minus 4x is plus 2x, and that's not right. So the 1 minus 4 combination doesn't work with the 6x and the x. So let's go to the next possibility, and the next possibility is minus 1 and plus 4. And let's check the cross term here. 6x times 4 is 24x. Minus 1 times x is minus x. That gives us 23x. That's not what we want, so that doesn't work. And we have to try the minus 1 and plus 4 in the other order. That is, make this one a plus 4 and this a minus 1. And once again, we check. 6x times minus 1 is minus 6x. Plus 4x is minus 2x. And that doesn't work. Well, we've tried this one. We've tried this one. Neither one of them works. So let's go to the possibility of plus 2 and minus 2. And we'll start this way. And we check the cross term again. 6x times minus 2 is minus 12x. Plus 2x is minus 10x. And that's not right. But we're still not done with the 2 and minus 2 because we could make it minus 2 over here and plus 2 over here. And we try again. 6x times 2 is 12x. Minus 2 times x is minus 2x. That's 12x plus minus 2x is 10x. And that's still not right. And we've tried every possibility that we can with all these factors. So this is clearly not correct. And we have to go to the possibility of 3x and 2x. And once again, we go back and start over with 1 and minus 4. So let's try it, 1 and minus 4. And we check the cross term. 3x times minus 4 is minus 12x. 1 times 2x is plus 2x. Minus 12x plus 2x is minus 10x. That's no good, but we can try these same two numbers in the other order. That is, put the minus 4 over here and the plus 1 over here. And now we check the cross term once again. 3x times plus 1 is plus 3x. Minus 4 times 2x is minus 8x. So we have plus 3x minus 8x. Plus 3x minus 8x. That's exactly minus 5x. So this really is the one we want. Perseverance pays off. We got to the right result, Now we don't ever have to bother to check these other possibilities because we've got the right one. So let's stop right here. We have 3x minus 4 times 2x plus 1. In this set of examples, the instructions in your study guide are factor completely. Factoring completely usually means that you're going to have to factor more than once, and you're probably going to have to use more than one type of factoring. If we take a look at number 1, we see we have 4x squared minus 4. Now, the first thing we're going to look for, the simplest kind of factoring, is monomial factoring, that is, removing a common factor. In this case, 4x squared contains the factor 4, and minus 4 contains the factor 4. Is that right? Because that's really 4 times minus 1. So we first factor the 4, writing this as 4 times x squared minus 1. Having done that, we recognize that x squared minus 1 is the difference of two squares, right? This is really x squared minus 1 squared. And we know how to factor the difference of two squares, so this is 4 times x minus 1 times x plus 1. And you see we use two types of factoring successively, the common factor first, and then we factored the difference of the two squares. In problem 2, we have a trinomial, y cubed plus 2y squared minus 15y. And again, the first thing we want to do is look for any common factor. Well, if you look, every term contains some power of y. And you know that you can factor out the lowest power of y, in this case, y to the first power, or just y. So we take out the common factor y, and what remains is from y cubed, we have y squared. From 2y squared, we're left with the 2y. And from the minus 15y, we're left with minus 15. So now we have y times a trinomial, and we can factor this trinomial, maybe. Well, this time we can. What are the factors? Well, we know what we're going to get. We're going to get y times y plus something times y plus something. But actually, one of the pluses is going to be a minus because we need two numbers whose product is minus 15 and whose sum is plus 2. And the natural factors to take of 15 are what? 5 and 3. Since we want to come out with a plus 2y, we're going to take plus 5 and minus 3. Now let's just check that that's right. Check. This is y squared. This is minus 3y plus 5y is plus 2y, and plus 5 times minus 3 is minus 15. So this expression is the product of three factors, y plus 5, and y minus 3. In example 3, we have a similar looking trinomial. We have ax squared minus 5ax minus 6a. We look for a common factor once again. In this case, the common factor is a. Every term contains the factor a. So we factor the a, and what's left behind is x squared, right? A times x squared is ax squared, minus 5x. Notice the a is in the middle here, but that doesn't matter. It's the product of 5 and a and x. So if we take out the a, we're just left with the 5 times the x, minus 5, of course. And when we factor the a from the minus 6a, of course, we just have minus 6. Once again, we've taken out a common factor, and what remains is a trinomial. And we're going to factor that trinomial. That's going to be x plus something times x plus something. And what factors are we going to use? Well, 6 can be factored as 3 times 2 or 6 times 1. Of course, here we want to get minus 6. We've got to take 1 plus and 1 minus. All right? What are we going to take? Well, a little bit of analysis. We think ahead, and we realize that we want the two factors. The product should be minus 6. The sum should be minus 5. All right? Let's try this. Minus 6 here and plus 1 here. If that doesn't work, we'll try something else. All right? We have x squared. Here's a minus 6x plus x. Minus 6x plus 1x is minus 5x. And minus 6 times plus 1 is minus 6. And we have the complete factorization, a times x minus 6 times x plus 1. Problem 4 is a nice problem. R to the 4th minus 16 has to be completely factored. All right? The first thing we do is realize that, in fact, this is the difference of squares, because this is r squared squared minus 4 squared. All right? Now, we know the difference of two squares. This is r squared minus 4 times r squared plus 4. But are we done? Well, no, we're not, because this first factor is itself the difference of two squares. This is r squared minus 2 squared. What about the other factor, r squared plus 4? No, we can't factor the sum of two squares, but we can factor the difference of two squares. And let's do it. R squared minus 4, remember that's r squared minus 2 squared, so that's r minus 2 times r plus 2 times r squared plus 4. Look again. This is a simple binomial, this is a simple binomial, and this is the sum of two squares, which doesn't factor, so we have factored r to the 4th minus 16 completely as r minus 2 times r plus 2 times r squared plus 4. In this section, we're going to work with algebraic fractions. The first thing we're going to do is reduce algebraic fractions to lowest terms. And of course, we reduce algebraic fractions the same way we reduce numerical fractions. And that is, we can cancel out, that is, divide out, common factors in numerator and denominator. More formally, factor both its numerator and its denominator. Divide both the numerator and the denominator by their greatest common factor. If we take a look at problem 1, we have a monomial, 8xy cubed, divided by another monomial, minus 24x to the 5th y. Now, we've done problems like this before, so let's get right at it. We cancel common factors in numerator and denominator. Well, first of all, we have a factor of 8 in the numerator and a minus 24 in the denominator. So we can divide out the 8, leaving a factor of 1 up here. Dividing 8 into minus 24 leaves a factor of minus 3 in the denominator. We have a factor x in the numerator and an x to the 5th in the denominator, so we can divide out the x, leaving another factor of 1. And that x divided into x to the 5th leaves us x to the 4th. So we've divided out the common factor x there. And we divide out a common factor y. There's a y in the denominator. We leave a factor of 1. And when we divide the y out here, we leave simply y to the 2nd power. Now, that doesn't look too neat, so let's recopy it. We have a 1 times a 1 times a y to the 2nd power. So the numerator is simply y to the 2nd power. In the denominator, we have the factor minus 3, x to the 4th. And of course, we did divide out that one factor of y. There's only a 1 left, so we don't bother to write it. Y squared divided by minus 3x to the 4th. Now, it is traditional not to leave fractions with a negative sign like this in the denominator, so we'll rewrite it as simply minus the fraction y squared over 3x to the 4th. Problem 2, we have a binomial, 8a minus 18, divided by the monomial 6. Now, we've done these problems earlier by short division, but this time we're going to do it by dividing out common factors. In order to do that, of course, I have to look at the factors that I have in numerator and denominator. Well, in the denominator, we have the number 6, so I think I'll just recopy that. But in the numerator, I can remove a common factor of 2 from each of the two terms. This is 2 times 4a minus 9. Okay, that's a proper factorization. 2 times 4a minus 9 equals 8a minus 18. And now you can see a common factor. There's a factor of 2 in this numerator, and the denominator, 6, is of course 3 times 2. So I can divide out the common factor 2 here and here, leaving just the 3. So this reduces to 4a minus 9 divided by 3. And there is no other common factor that can be divided out. Now notice, a lot of people would like to divide this 3 into this 9. But the 4a is not being multiplied by the minus 9. So it's not a factor. These are added. And you can't cancel a factor in the denominator with 1 into one of the terms in the numerator. It must be a common factor of the entire numerator. Problem 3, we have x plus y squared divided by y squared minus x squared. Well, if we're going to divide out common factors, we better know what they are. X plus y squared is really x plus y times x plus y. Now, it's not really necessary to write out both those factors, but just this time I'd like you to really look at them. Y squared minus x squared is the difference of 2 squares, and it factors as y minus x times y plus x. Now, at first blush, it doesn't look like there's any common factor in numerator and denominator. But at second look, you see that in the numerator I have x plus y. In the denominator I have y plus x. Well, x plus y and y plus x are really the same thing. It doesn't matter which order you add things. So therefore, these factors, x plus y and y plus x, are really the same numbers. And they can be divided out. Notice if there was a minus sign, they'd be different, but it's a plus sign. So we really can cancel these out, and we're left with x plus y divided by y minus x. In example 4, we have x squared minus 5x divided by x squared minus 2x minus 15. And here we really have some factoring to do. In the numerator, we have a common factor of x, so we have x times x minus 5. The denominator is a trinomial, which factors into 2 binomials. Of course, the product of the numbers out here is going to have to be 15, or minus 15, and the summas have to be minus 2, and it's easy to see that the factors we want are these, x minus 5 times x plus 3. Let's just check that cross term. Minus 5x plus 3x is minus 2x. Now, once we factor the numerator and denominator, the common factor is easy to see. The common factor is x minus 5 in numerator and denominator. So we've reduced this fraction to simply x divided by x plus 3. And once again, we cannot cancel this x with this x because this is not a factor here. This is a term. These are added together. Now we're going to multiply some fractions. Now again, you know from working with ordinary numbers that when you multiply fractions, you multiply the numerators and you multiply the denominators, which really means that the biggest job in multiplying algebraic fractions is going to be the reduction to simplest terms when we're through. Here's what we do. Factor the numerators and denominators of the fractions. Divide the numerators and the denominators by common factors. Multiply the remaining factors of the numerators and the denominators. For example, if you look at number 1, you have the fraction 8r squared divided by 14s squared times the fraction 7s to the 4th divided by 2r. Now, when we multiply the two fractions, as I said, we simply multiply the numerators together and we multiply the denominators together. So really we have this, 8r squared divided by 8r squared times 7s to the 4th divided by 14s squared times 2r. Now, of course, we could do this multiplication out, but there's no need to because we're going to be dividing out common factors, so we might as well divide them out right away. 2 and 8 have a common factor of 2, so we can divide a 2 out of the denominator. Dividing it into the 8 here, we get a 4. Similarly, The 7 and 14 can be taken care of. 7 divided in here just leaves you a factor of 1, and 7 into 14 leaves a factor of 2. All right? Now let's see, what can we do with the variables? We have an r here and an r squared up here. So we can divide out an r, reducing this to r to the first power. And we have an s squared here and an s to the fourth in the numerator. So we can divide out an s squared, leaving just an s to the second power in the numerator. And now let's see if we can get everything together. We left a factor of 4 up here and a factor of r times s squared over here. And in the denominator, we still have left a 2, which means I missed a factor because I have a common factor of 2 in the 4 here. So I can yet divide through this 2 and leave the result simply 2rs squared. All right? If you see all the factors right away, that makes it easier. If you miss one, you can always recover because you'll see it in the next step. In number 2, we have the product of two fractions that look rather complicated. We have a trinomial in the numerator and a binomial denominator in the first one, and binomials in numerator and denominator in the second one. Once again, remember that what we really have here is the product of this numerator times this numerator, and the product of this denominator times this denominator. So really, we have the product of many different factors in top and bottom, and the way to see what they are is to factor everything that we recognize the factors of. X squared minus 4x minus 12 is a trinomial, which you can factor by trial and error, and you'll get what? X minus 6 times x plus 2, I believe. Let's check that. This is x squared minus 6x plus 2x is minus 4x. Minus 6 times plus 2 is minus 12. That's the correct factorization. In this one, we have a common factor of x in both terms. So we factor an x times 2 minus x. In the denominator, we have 2x minus 4, from which we can factor a 2 and write this as 2 times x minus 2. And here we simply have the binomial x plus 2. Now let's see if there are any common factors in the numerator and denominator that divide out. Well, first of all, there's an x plus 2 here and an x plus 2 here. Numerator, denominator cancel out. And it looks like that's all we have, except there is another one, and it's a subtle one. Here we have the factor 2 minus x. And here we have the factor x minus 2. Well, x minus 2 and 2 minus x look awfully close. And indeed, they are awfully close, because this is true. If you take x minus 2 and multiply it by minus 1, the result is equal to minus x plus 2, which you could rewrite as 2 minus x. So in fact, x minus 2 times minus 1 is 2 minus x. In other words, 2 minus x divided by x minus 2 is simply minus 1. All right? So they really are almost a common factor. In fact, they are common factors. One is simply the other one multiplied by minus 1. The result is that I can go back to my original problem here and realize that if I have 2 minus x in the numerator and x minus 2 in the denominator, that really divides through, leaving the factor minus 1. All right, now let's summarize what we have here. We have minus 1 times x minus 6 times x in the numerator. And in the denominator, we have left only a 2. And of course, most people wouldn't want to write that minus 1, so we'll simply write this as minus the fraction x minus 6 times x over 2. Now we'll do some division problems. First thing you have to understand is how one divides fractions. Well, of course, you know how to divide fractions. When you divide one fraction by another, all you really do is invert the divisor, that's the second one, and then multiply. So for example, here we have x squared plus 2x minus 3 divided by x squared plus 7x plus 10, a trinomial over a trinomial, divided by a trinomial over a binomial. And of course, what we're going to do is we're going to do the division by inverting this divisor and then multiplying. Now, we know that when we do a multiplication problem, we simply multiply the numerators together and we multiply the denominators together. So that really the main work is in the reduction of the fraction, which means we're going to have to factor it. So to save a little bit of time and space, what I'm going to do is copy this as a multiplication problem, and I'm going to factor at the same time. So x squared plus 2x minus 3 has two binomial factors, and they are x plus 3 times x minus 1. All right? The denominator, x squared plus 7x plus 10, can also be factored into binomials. It's x plus 5 times x plus 2. And we're multiplying this by this fraction flipped over, inverted. All right? So let me look at the factors. Remember, this is going to become the top. And the factors of x squared minus 25, that's a difference of squares. So it's x minus 5 times x plus 5. This numerator becomes the denominator after we invert. And its factors are x plus 3 times x plus 3. And now we start looking for common factors in numerator and denominator. Well, let's see. There's an x plus 3 here, and there's an x plus 3 here. So we can divide that out. There's an x plus 5 in the denominator here and an x plus 5 in the numerator here. So that divides out. And if you look at what's left, you see that there are no more factors common to numerator and denominator. So we write this as x minus 1 times x minus 5 divided by x plus 2 times x plus 3. Now, this is a perfectly good answer, but of course many people would like to see it written as a trinomial over a trinomial, because that was really the form in which the problem was originally presented to us. So let's just multiply this out and show you what an alternate form of the answer would look like. This is x squared minus 5x minus x is minus 6x. Minus 1 times minus 5 is plus 5. So we have x squared minus 6x plus 5. And in the denominator, we get x squared. 3x plus 2x is 5x. 2 plus 3, 2 times 3 is plus 6. So we could have left the answer in this form, a trinomial divided by a trinomial. In problem 2, we have a trinomial divided by the square of a binomial, and this whole fraction is divided by x minus 2. Now, you can do this division if you realize that x minus 2 is in fact a fraction. It's a fraction with denominator 1. Think of this as x minus 2 divided by 1. Then you can reduce the problem to a multiplication problem where we're going to invert this divisor. We're going to invert this fraction and multiply. So let's do this one the way we did the last. We'll factor this numerator as we write it down. This is really x minus 2 times x minus 3. The denominator is x minus 3 squared, which again I could have written as x minus 3 times x minus 3. And this is multiplied by the reciprocal of this fraction, that is 1 over x minus 2. And now we look for common factors, numerator and denominator. We have an x minus 2 in the numerator here and an x minus 2 in the denominator there, and that can be divided out. Then we have an x minus 3 in the numerator and an x minus 3 squared in the denominator, which means we can divide out the x minus 3, leaving up here really only a 1. And dividing an x minus 3 into an x minus 3 squared just leaves x minus 3 to the first power. So this reduces to 1 divided by x minus 3 to the first power, which is, of course, just x minus 3. So our result is 1 over x minus 3. Let's look at some examples involving addition and subtraction of algebraic fractions. Now we add algebraic fractions in essentially the same way we add ordinary numerical fractions. Remember, when you add numerical fractions, you have to have both fractions with the same denominator. So for example, 2/7 plus 3/7 adds up to 5/7, and what do you really do? When adding fractions, keep the common denominator and add the numerators. Or when subtracting, keep the common denominator and subtract the numerators. We're going to do the same thing with algebraic fractions. In example 1, we have a over a plus b over a plus b. These two fractions have the same denominator. The denominator is this binomial a plus b. And therefore, we can add these fractions just the same way we would have added them if they were numbers. We retain the common denominator a plus b, and we add the numerators. The numerator of the first fraction is a plus the numerator of the second fraction, which is plus b. So we have a plus b over a plus b. And again, just as with ordinary numerical fractions, we always reduce fractions to lowest terms. Here we have a plus b over a plus b, and of course anything divided by itself is 1. So this simply reduces to the number 1. If we look at example 2, we have two fractions with the same denominator, 2x plus 6, which means we can combine these fractions by, in this case, subtraction, all right, by simply subtracting the numerator of the second fraction from the numerator of the first fraction, retaining the common denominator. So let me just write this. Common denominator is 2x plus 6. Now we have from the first fraction 8x plus 2, and then we have minus this entire numerator, and this is 5x minus 7. All right, now we're going to try to simplify a little. First thing we're going to do is remove these parentheses. So we have 8x plus 2. Now this, remember, is really plus 5x minus 7. There's a minus in front, so we change the signs of both terms. That becomes minus 5x plus 7. And of course, we still have the denominator 2x plus 6. Now we combine like terms in the numerator. 8x minus 5x is 3x. 2 plus 7 is 9. So we have 3x plus 9 divided by 2x plus 6. And now we're going to attempt to reduce to lowest terms. In order to do that, I have to see what the factors of the numerator and the denominator are. Well, in the numerator, there's a common factor of 3. So I can make this 3 times x plus 3. And in the denominator, I have a common factor of 2. And I can factor that 2 and make it 2 times x plus 3. And if you look, you see I have the same binomial factor, numerator and denominator. I have x plus 3 over x plus 3. And that can be divided out so that this entire expression reduces to simply the number 3 over 2. In problem 3, we have our first example of the subtraction of one fraction from another where the fractions have different denominators. We have 2 over x minus 3 over y. When adding or subtracting fractions with different denominators, first find the least common denominator and rewrite each fraction as an equivalent fraction with that common denominator. Then you may combine the fractions. Now, let's take a look at an equivalent numerical problem. Remember back in elementary school, you might have had to add, say, 2/3 plus 4/5. You can't just add the numerators because the denominators are not the same. But what you can do is you can make the denominators the same because you know that you can multiply the top and bottom of a fraction by the same number without changing the fraction. In essence, you're multiplying by 1. So what you try to do is get both these fractions to have the same denominator. In this case, the denominator you're going to aim for is 15, which is the product of 3 and 5. So the first fraction, you multiply top and bottom by 5. That really then becomes 10/15. The second fraction, you multiply top and bottom by 3, so that you have actually 12/15. So now you have 10/15 plus 12/15, and that adds up to 22/15. All right? Let's see if we can do the same thing with letters. If we look at problem 3 once again, we see we have 2 over x minus 3 over y. The common denominator that I can achieve is x times y. And how do I do that? I multiply the first fraction by y over y, actually. Multiply the top by y and the bottom by y. You realize multiplying by y over y is really multiplying by 1, so I'm not really changing the fraction. The other one, you say, I want to get the denominator x times y. I've written here y times x. So I'll multiply top and bottom here by x. And now you see, in both cases, the denominator is going to be y times x, or you could write it as x times y, which is what I'm going to do because most people write things alphabetically. So it's x times y. And in the numerator, what do I have? I have 2y minus 3x. I realize that looks like y times 2, but again, we know we can write that as 2y. So you see we now have 2y minus 3x over this common denominator, xy. If we look at example 4, we have the same kind of problem. We have 5 over x plus 7 over x cubed. And of course, if I want to use exactly the same method I used before, I would take as the common denominator the product of these two numbers, x and x cubed. But again, remember, when you were doing these things with numbers, if you had to add, say, 2/3 plus 5/6, you didn't use the common denominator 18, which was the product of 3 and 6. You used the common denominator 6, because 3, you see, is a factor of the number 6. So you only really have to multiply this fraction by 2 over 2, so that you get the common denominator 6. So this then becomes 4 over 6 plus 5 over 6, which is 9 over 6, which of course you would then reduce to 3 over 2, but that's another story. In problem 4, we have 5 over x plus 7 over x cubed. I can get the common denominator x cubed by simply multiplying top and bottom of this first fraction by x squared. Now you see I have the common denominator x cubed for the two fractions, and I can simply combine the numerators by addition. This is x squared times 5, which is 5x squared, and this numerator is simply 7. So I have 5x squared plus 7 over x cubed. In example 5, we have 3 over a squared b plus 2 over ab squared. Now let's see what we have to do to get a common denominator for these two fractions. If you look, this first fraction has a factor a squared in the denominator. The second fraction has only an a. We'd like them both to have a squared, which means I want to multiply this second fraction denominator by a. But of course, if I multiply the denominator by a, I must also multiply the numerator by a. Now look, I have a squared b squared here. Here I have a squared times b, and of course I would like this to also be b squared. So I'm going to multiply the denominator here by b. And again, when I do that, I must also multiply the numerator by b. Now you see both fractions really have the common denominator a squared b squared. Doesn't look it. This is a squared b times b. That's a squared b squared. This is a b squared times a. That's also a squared b squared. Since we have the common denominator a squared b squared, I can add the fractions by simply adding the numerators. And the numerators are now what? Well, this one is 3b plus this one is 2a. So we have 3b plus 2a over a squared b squared. In number 6, we have two fractions. We have a binomial divided by 3 minus another binomial divided by 2. And of course, to get a common denominator for these two fractions, we're going to use 2 times 3. That means I have to multiply this fraction denominator by 2, which means I multiply top and bottom by 2. Now notice I'm putting it in parentheses so you really can see. I multiply the denominator by 2. I multiply the entire numerator by 2. The numerator is a binomial, so I put it in parentheses to show that I'm multiplying the whole thing by 2. In the second fraction, I multiply the denominator by 3. That means I also multiply the numerator by 3. Now notice that minus sign was not in front of the x, it was in front of the entire fraction, so I'm really multiplying the binomial plus x minus 1 by 3. Now you see we have the common denominator 6, so I can simply combine the numerators, in this case by subtraction. So I have 2 times 3x plus 5 minus 3 times x minus 1. Now, I'll multiply out, expand, and combine like terms. Denominator is 6. In the numerator, I have 6x plus 10. And here I have minus 3x. Minus 3 times minus 1 is plus 3. And now we combine the like terms, as I said. 6x minus 3x is 3x. Plus 10 plus 3 is 13. The whole thing divided by 6. Now, don't be tempted to try to cancel that 3 into this 6. These two terms are added together, and you can only cancel common factors from numerator and denominator. 3 is not a factor of the entire numerator, and therefore it cannot be divided out. In problem 7, we have a fraction minus a monomial. This will be the equivalent in numbers of a fraction minus a whole number. And of course, the way we handle that is to realize that the monomial, 3c, can be thought of as a fraction, that is 3c divided by 1. And now you see you have a fraction minus a fraction. One of the denominators is 1. And if we want to make these things have a common denominator, all we have to do is multiply the denominator of the second fraction by 4. So they'll both have denominator 4. So I simply multiply it by 4. But of course, that means I also multiply the numerator by 4. Remember, you've got to do the same multiplication top and bottom, or you're going to change the value of the fraction. Now I haven't changed anything. I have a common denominator 4, and I can simply combine these numerators by addition. In this case, actually, it's addition of a negative thing. So we have 5c minus 2, and here we have minus 3c times 4 is 12c. And now I'll combine like terms, and I have 4 in the denominator, and in the numerator I have 5c minus 12c is minus 7c minus 2. In example 8, we have 7 over x minus 4 plus 5 over 2x minus 8. Now, if I'd like to find a common denominator here, what I really should do is look at the factors of this second denominator. See, the first one is just x minus 4. The second can actually be factored. It's actually 2 times x minus 4. Now, if you think of 2x minus 8 as 2 times x minus 4, or if you simply noticed from the very outset that this denominator was simply twice this one, you do the same thing. That is, to get a common denominator, you want to multiply the denominator of this first fraction by 2. Of course, if you multiply the denominator by 2, you multiply the numerator by 2. So now what I have is two fractions with the common denominator 2 times x minus 4, or you could write it as 2x minus 8. It doesn't matter which. In the numerator, you have 2 times 7 is 14, plus this numerator, which is 5. So we simply have 19 divided by 2 times x minus 4. And the one advantage of leaving it in factored form here is that if there were a common factor in the numerator that I could divide out, I would see it immediately. Here I can see there is no common factor, and the answer is 19 divided by 2 times x minus 4. In example 9, I have, again, two fractions with dissimilar looking denominators. And once again, the key to finding a common denominator is to see the factors of this first one. So let's see what they are. This denominator you recognize as the difference of squares, y squared minus 16, and that's y minus 4 times y plus 4. The second fraction is just 3 divided by y minus 4. And you can see that I can make these two denominators the same by simply multiplying the second one by the missing factor. Here I have y minus 4 times y plus 4. Here I have only y minus 4, so I want to multiply by y plus 4. Again, that means multiply the numerator by y plus 4 as well. Now we have a common denominator, which is y minus 4 times y plus 4. And in the numerator, I have 5 plus 3 times y plus 4, which is simply 3y plus 12. Combining like terms in the numerator, I have 3y plus 17 over y minus 4 times y plus 4. In problem 10, we have the same kind of situation, two dissimilar denominators. But here, you see there's no factoring to be done. Here I have c plus 4 in the denominator, and here I have just c in the denominator. Now don't, whatever you do, be tempted to add a plus 4 down here and a plus 4 up here. That's simply not allowed. You cannot change a fraction by adding the same thing to both numerator and denominator. That changes the value of the fraction, and that you're not allowed to do. So therefore, to get a least common denominator, what you must do is multiply this denominator by c, which means multiply this numerator by c, and multiply this denominator by the missing factor c plus 4, which means multiplying this numerator by c plus 4. Now you see we have a common denominator, a proper common denominator, c times c plus 4. And let's see what we have in the numerator. Here we have 8c, and here we have minus the quantity 2 times c plus 4. We remove parentheses. We have 8c minus 2c minus 8 divided by c times c plus 4. And we combine like terms. 8c minus 2c is 6c minus 8, the whole thing over c times c plus 4. Now, very quickly, I'm just going to look. There is a common factor of 2 here, so I could write this as 2 times 3c minus 4, but that doesn't give me any of the factors of the denominator, so I can't reduce this fraction below what it is here. When solving equations that involve fractions, usually your best bet is to try to get rid of the fractions as soon as possible. To eliminate fractions in an equation, multiply both sides of the equation by the least common multiple of the denominators that appear. This will cancel out all the denominators. For example, we look at a very simple one in number 1. X plus 3 divided by 5 equals 7. Now here we have a fraction on the left-hand side, and what I would like to do is get rid of that denominator 5. And of course, the way to get rid of the denominator 5 is to multiply the fraction by 5. Is that right? Because really, if you multiply by 5 as if you have 5 times 1/5, the 5's go out and you're just left with the 1. Well, it's the same thing for any other fraction. If this were 5 times 4/5, you'd be left with just the 4, for example. So in our case, we have x plus 3 over 5 equals 7. To get rid of that 5, I want to multiply this side of the equation by 5. Of course, that means I have to multiply the right-hand side by 5 also. Now the 5's go out, and you're left over here with just x plus 3, and you're left over here with 7 times 5, which is 35. Now, of course, we simply subtract 3 from both sides of this equation, as we've done many times in the past, and we get x is equal to 32. And of course, you should check answers. Let's check this one in our heads because it's really a very quick check. We originally had x plus 3 over 5. X plus 3 is 32 plus 3 is 35. 35 over 5 is 7, and that was the original equation if you look back. In example 2, we have x over 2 plus x over 3 equals 1. Now here we'd like to multiply this entire equation by some number that will eliminate both of the denominators. Now think about what I'm saying. I'm going to multiply the equation, that is both sides, by some number that will eliminate both denominators. That really means I need something that has 2 as one of its factors and 3 as one of its factors. And the simplest number I can think of is 6. So I multiply the left-hand side by 6, and I multiply the right-hand side by 6. Now what happens when I multiply x over 2 by 6? Let me just write that down. This is 6 times x over 2. The 2 divides into the 6, giving me a 3, so that this term really becomes 3x. At the same time, I'm multiplying this second term over here by 6, so I really have 6 times x over 3, and the 3 divides out, leaving me just the 2. So in fact, this first term has become 3x, and the second term has become 2x. And of course, it's equal to 1 times 6, or 6. Let me rewrite that neatly. That's 3x plus 2x equals 6. That's 5x equals 6. And dividing by 5, I get x equals 6/5. In number 3, we have 2 fractions on the left-hand side and a fraction on the right-hand side. Notice the denominators, because that's what we want to get rid of. We have a 4, a 3, and a 6. I have to multiply by some number that will contain among its factors 4, 3, and 6. For example, I could multiply through by 24. 4 divides into 24, 3 divides into 24, 6 divides into 24, and I'll cancel out those denominators. But of course, if I want the numbers to stay small, I should use the smallest number that I can think of that would have each of these as its factors. That would be known as the least common multiple of these numbers, 4, 3, and 6. And that's when you probably can guess easily that's 12. So I want to multiply the left-hand side of the equation by 12 and the right-hand side by 12. And now let's see what happens. In a manner similar to what I had in the previous example, when I multiply this first term by 12, the 4 divides into the 12, and I just have left a 3 times that numerator, y plus 3. Then I have a minus sign. When I multiply this second term by 12, what happens? Well, the 3 divides into the 12, leaving behind the factor 4. So I have 4 times this numerator, y minus 4. On the right-hand side, of course, the 6 divides into the 12, giving 2, and 2 times 11 is 22. All right, let's expand. This is 3y plus 9 minus what? 4y minus 4 times minus 4 is plus 16 equals 22. Combine like terms. 3y minus 4y is minus y. 9 plus 16 is 25 equals 22. Subtract 25 from both sides of the equation and get minus y equals minus 3. And of course, if minus y equals minus 3, we've seen this many times in the past, y is simply equal to 3. So the solution is y equals 3, and you should really check this before you stop. In example 4, we have an equation that involves a fraction. In this case, the unknown is in the denominator of the fraction. We have 12 over 2x plus 1 equals 4. But we can still do it in the same way. We're going to multiply both sides of the equation by the same quantity. The quantity we want to choose is one that will eliminate the denominator. Well, how do we eliminate the denominator 2x plus 1? we have to multiply this fraction by 2x plus 1. Of course, that means whatever we do, remember, on the left side, we also have to do on the right side. So I multiply both sides of the equation by 2x plus 1. Now you see, really, that's the quantity 2x plus 1 here, the quantity 2x plus 1 here. Cancel out the like factor top and bottom, and I have simply 12 is equal to, and on the right-hand side, I have 4 times 2x plus 1, which is 8x plus 4. Now I subtract 4 from both sides of the equation, get 8x equals 8, and divide by 8, and get x equals 1. All right, quick check. We originally had 12 over 2x plus 1. If x is 1, that's 12 over 3, which is 4. And indeed, the original equation, it was equal to 4. In example 5, we have the unknown in the denominator on the left and also on the right. If I want to eliminate these denominators, what I have to do is multiply by the product of the two of them. Just as when I was working with thirds and fifths, I had to use a denominator 15, which is 3 times 5. Here I have to get both factors, so I'm going to multiply both sides of the equation by y times 5 minus y. Okay? Y and 5 minus y. Now we take a look and see what happens. Here we have common factors y that divide out. Here we have common factors 5 minus y that divide out. On the left-hand side, that leaves us 3 times 5 minus y. Let me write that. Equals, on the right-hand side, 2y. Multiply out. Now I have 15 minus 3y equals 2y. Add 3y to both sides. And we have 15 equals 5y, and divide by 5, and get y equals 3. Now let me look at this problem again in a slightly different way. Let me just rewrite it. It was 3 over y equals 2 over 5 minus y. I could think of this as a proportion. 3 is to y as 2 is to 5 minus y. And in a proportion, you know, the product of the means equals the product of the extremes. In other words, this number 3 times this number 5 minus y is the same as this number 2 times this number y. Or, for short, we say we can cross-multiply. You multiply this times this, and that has to equal this times this. Now, that's pretty messy looking, but let me see if I can rewrite it. This is 3 times 5 minus y equals 2 times y. Now, actually, you see, that's the same equation that we just had over here, but it's just a little bit quicker to do the cross multiplication than to look for this common multiple to multiply by. I'm not going to go through solving again. I've done it once. Now, look, if I had had that idea before, I could have looked at equation problem number 4. Remember, in problem number 4, let me go back over here. I had 12 over 2x plus 1 is equal to 4. I could have thought of 4 as 4 over 1. And then I could have done this one also by cross multiplication. This would be 12 times 1 is 12 is equal to 4 times 2x plus 1. And once again, that's the equation that I had. Well, I actually had it expanded over here, so let me expand it. That's 12 equals 8x plus 4. And I have the same equation that I got back here. So you see, you can always, if you have only one fraction on the left and one fraction on the right, you can always do the problem by cross multiplication, and that's a nice, quick way to do it. Problem 6 doesn't look like a fractional equation, but it really is, because the coefficients in problem 6 are decimals, and decimals are really fractions. Here we have 0.13x. Well, 0.13, you see, is really 13 over 100. And here we have a minus, of course that's really an x, we have a minus 1.3, and 1.3 is 13 over 10. So we really have 13 over 100x minus 13 over 10. On the other side, we have 0.08x, which is really 8 over 100 times x. And 7.7 is really 77 over 10. Now, if I want to get rid of all these denominators, what I really want to do is multiply this by 100. But of course, if I'm going to multiply one thing by 100, I've got to multiply everything by 100. 10 would have been sufficient here, but I can't do one of them by 100 and one by 10. So I'll have to write hundreds in each of these places, and then I'll be able to cancel 100 into 100, a 10 into 100, 100 into 100, 10 into 100, and so on. But let's actually do it on the equation that we started with. Here we have decimals. My understanding is that I want to multiply everything by 100 to get rid of the decimals, just as I did with the fractions. So I multiply the left-hand side of the equation by 100, and I multiply the right-hand side of the equation by 100. Now let's see what happens. Multiply this by 100. 100 times 0.13 moves the decimal place 2 positions, and I get 13x. 100 times 1.3 moves the decimal 2 positions. Well, 1 position gets me here, so I have to add a 0. So this becomes minus 130. On the right-hand side, 100 times 0.08 moves the decimal, gives me 8x. And 100 times 7.7, again, I'm going to have to add a 0 in order to move it. So I get 770. All right? Add 130 to both sides of the equation, and I get 13x equals 8x plus 130 plus 770 is 900. And then subtract 8x from both sides. Well, that is add minus 8x, and I get 5x equals 900. And divide by 5, we have x equals 180. Let's look at one verbal problem that leads to a fractional equation. Number 7 says, the denominator of a fraction is 1 more than twice the numerator. If the numerator is decreased by 1 and the denominator is increased by 1, the value of the resulting fraction is 1/4. Find the original fraction. Well, let's identify some unknowns. Let x be the numerator of the original fraction, remember, of the original fraction. Now, it says the denominator is 1 more than twice the numerator. So 2x plus 1, that's twice the numerator plus 1, is going to equal the denominator of that same original fraction. So the original fraction is this. The original fraction is equal to x divided by 2x plus 1. Now the problem says that the numerator is decreased by 1 and the denominator is increased by 1. Well, what does that mean? That means we take the numerator and we subtract 1 from it. So the numerator is x minus 1, and the denominator is increased by 1. That means we add 1 to the denominator. That's 2x plus 1 plus 1. And the resulting fraction is equal to 1/4 in value. All right? Let me just combine these terms here. So I have x minus 1 over 2x plus 2 is equal to 1/4. And now we'll use that little cross multiplication trick that we had before. We take x minus 1 times 4, that's 4 times x minus 1, is equal to 1 times 2x plus 2. That's a very bad 2. All right. Now we'll expand, and we have 4x minus 4 is equal to 2x plus 2. Add 4 to both sides. We have 4x equals 2x plus 6. subtract 2x from both sides, and we have 2x equals 6. Divide by 2, and we have x equals 3. Now, are we really finished when we say x equals 3? Well, no. You see, the question said, find the original fraction. Now, the original fraction is x divided by 2x plus 1. So if we want to really know what the original fraction was, we have to take this expression and substitute into it the value of x we just found. And the value of x we just found was 3. So the original fraction was actually 3 divided by 2 times 3 plus 1. In other words, 3 over 7. So our original fraction was 3/7. And let's just check that. If we decrease this numerator by 1, it becomes 2. And if we increase this denominator by 1, it becomes 8. And 2 over 8 is exactly equal to 1/4. In this section, we're going to discuss the topic of radicals. Now, a radical really means a root, just as in the word radish. It means a root. If we look at problem 1, it says the square root of 36 equals what? Well, square root of 36, what does that really mean? The symbol is a radical, and it indicates we're supposed to find the square root of the number under the radical. Now, the square root of a number is one of the 2 equal factors of the number. Do you understand that? We can take 36 and factor it in many ways. We could factor it as 3 times 12, but those are not equal factors. Or we could make it 4 times 9, but those are not equal factors. But we could also make it 6 times 6, and those are 2 equal factors. So the square root of 36 we would call 6. But that's not the only possibility, because after all, minus 6 times minus 6 is also 36. So what do we mean? Well, it's understood that if there's no sign in front of the square root, we mean the positive square root. The positive square root is called the principal root. So the positive square root, the positive number such that that number multiplied by itself gives you 36, is simply 6. So the square root of 36 is 6. Sometimes, as in example 2, you really want the negative number, which would serve as a square root. If you want that, you indicate it, as in example 2, minus the square root, in this case of 144. Now, you should understand, or you should recognize, that 144 could be factored as 12 times 12. So the square root of 144 is 12. Again, minus 12 would do just as well. And in this case, because we have a minus sign out in front, we do take the answer to be minus 12, minus the principal root. Problem 3, we have a special symbol, plus or minus the square root of 625. First, you should understand that the plus or minus indicates that we're willing to accept either the plus or the minus as the root. And the square root of 625, well, you've got to ask yourself, what number multiplied by itself gives you the result 625? And of course, you all know that. You all know that 25 times 25 is 625. So in this case, we write our answer as plus or minus 25. Now, you must understand that this really means I have 2 different answers, 2 possible different answers. I have plus 25 or minus 25. That is, 625 could be thought of as plus 25 times plus 25, or minus 25 times minus 25. But not plus 25 times minus 25, because that gives you a negative answer. Is that right? Plus times a plus is plus. Minus times a minus is plus. So either of these could serve. And this plus or minus symbol indicates that we're willing to accept either the positive or the negative number that serves as the square root of 625. If you go to number 4, you have the square root of 25 over 81. Now that may look a little complicated, but actually all you have to do is ask what number, when multiplied by itself, will give you the fraction 25 over 81. You see, we don't only take square roots of whole numbers. We can also take square roots of fractions. But it's not hard to see what the right answer is. In order to get a 25 in the numerator, you must really have 5 times 5. And in order to get 81 in the denominator, you must really have 9 times 9. So the square root of 25 over 81 is simply 5 over 9. And once again, this is plus, because when no sign is indicated, we must take the positive square root. So the square root of 25 over 81 is 5 over 9. In problem 5, we have the square root of 0.04. Well, you can take the square root of decimals if you can recognize what the proper factors are, the proper equal factors. You must realize, of course, that the square root of a decimal is actually going to be a number that's larger than the decimal itself, because when you take a small number and square it, it gets smaller. So, in fact, the proper number that has to be multiplied by itself to get 0.04 as an answer is simply 0.2. Now check that one. 0.2 times 0.2 is 0.04. Make sure you understand that one. We might have to take square root of decimals at later points. In number 6, we have the square root of the quantity 9 squared. And although it may not seem obvious, my initial thought is to say, well, 9 squared is 9 times 9. So I actually have the equal factors, 9 times 9. And therefore, the square root of 9 squared must be just 9. And that's correct, all right? But be careful with that kind of problem, because you're always supposed to do what's inside the parentheses first. So you really should take 9 squared and get 81. That's all right. This is really the square root of 81, and the square root of 81 is 9. That's not a problem. In number 7, you see why I try to emphasize the fact that you should do what's inside the square root first. Because, again, here I have minus 7 squared. That's minus 7 times minus 7. And the tendency is to say that that should give you minus 7 as a square root. Let me say that again. I have minus 7 times minus 7. Those are two equal factors that give you minus 7 squared. And therefore, the square root would be minus 7. But you see, our rule says, first of all, that you should do what's inside the parentheses first. So this is really the square root of plus 49. Minus 7 times minus 7 is plus 49. Since there's a plus sign out in front, the square root of 49 is simply plus 7. So the square root of minus 7 squared is plus 7. And that's kind of a strange result, but you're going to have to get used to it. In example 8, we have a symbol that looks like a square root symbol, but just a little bit different, because you see there's a number up here, a little number 3. Now this 3 is called the index of the radical. Actually, your square roots had an index also. The index was 2. But the 2 is understood if it's not shown in a radical. So this is called the cube root of 8. And since the square root indicated, remember, by an understood index 2, the square root means one of 2 equal factors that give you the number. The cube root is one of 3 equal factors that give you the number. In other words, to find the cube root of 8, you're looking for a number which, when multiplied by itself and then by itself again, results in 8. All right? Let's see. What could that possibly be? Well, to get 8, I would have to take 2 times 2 times 2. In other words, 8 is the product of 3 2's, and therefore the cube root of 8 is simply 2. Now you notice with the cube root, I don't have to worry about the sign, because this can't possibly be minus 2, because minus 2 times minus 2 is plus 4. When I multiply once again by minus 2, I get minus 8, which is the wrong answer. I want to get plus 8. So with cube roots, I don't have that sign problem. It's understood the cube root of plus 8 is plus 2. In example 9, we have the cube root of minus 27. Now, you'll notice I never took the square root of any negative number. Square roots of negative numbers are handled in slightly higher level mathematics courses. But cube roots of negative numbers we can find, because here I need the product of three numbers the same, that result in minus 27. What number can I multiply by itself and then by itself again to result in minus 27? And the answer is minus 3, because minus 3 times minus 3 is plus 9 times another minus 3 is minus 27. So the cube root of the negative number is a negative number, and in this case that negative number is minus 3. In example 10, we have the fourth root of 81. You see here the index is not 3, it's 4. And again, what we want here is one of 4 equal factors that result in 81. What number raised to the 4th power is equal to 81? Well, there aren't many choices. 3 times 3 times 3 times 3 actually gives you 81. 3 times 3 is 9, times 3 again is 27, times 3 is 81. So the 4th root of 81 is 3. Now, the one thing you may be wondering is, how do you recognize all these perfect roots, perfect square roots, perfect cube roots, perfect 4th roots? And the answer is, you memorize tables of them. You memorize, for example, the first 20 perfect squares. So you know the square roots of numbers like 0, 1, 4, 9, 16, and so on. And you also have to memorize some perfect cubes and, indeed, some perfect 4th powers, but not too many, just enough to get through reasonable sized numbers like the 4th root of 81, possibly. Problem 11. Find the square root of 29. Well, up until now, we've only taken the square roots of perfect squares. That is, we've only taken the square roots of numbers that come out to yield either whole numbers or fractions as their square roots. All right? Whole numbers and fractions are called rational numbers. Now, remember what a rational number is. A rational number is any number that can be written in the form of a over b, where a and b are integers and b is not equal to 0. Every rational number can be expressed as either a terminating or repeating decimal. So, for example, 1/4 is 0.25. That's a terminating decimal. 1/3 is 0.333, etc. That's a repeating decimal. But the square root of 29 is neither a terminating nor a repeating decimal. It is an irrational number. An irrational number is any number that cannot be written in the form of a over b, where a and b are integers and b is not equal to 0. So the best we can really do is to estimate the square root of 29. That is, we can calculate the square root of 29 to as many decimal places as we want, but we really can never get to the end. Well, how do you really do it? Well, of course, the easy way to do it is to use some kind of mechanical aid. For example, there are tables of square roots. You look up the number 29 in the table, and in the table is printed the square root of 29 to a certain number of decimal places. Or you could use a calculator. Now, I took out my calculator, and I entered the number 29, and I pressed the square root button, and the calculator displayed 5.3851648. So to 7 decimal places, the square root of 29, according to my calculator, is 5.3851648. Well, that's easy. But suppose you don't have a calculator. Suppose you're expected to estimate the square root of 29 without any mechanical device. All right? You reason as follows. Step 1, you try to find two whole numbers that bound the square root of 29. What do I mean by bounded? Well, if you take the square root of 25, you get 5. If you take the square root of 36, you get 6. In other words, I find two perfect squares, in this case 25 and 36, one of which is less than 29 and one of which is just greater than 29. So the square root of 25 is 5. The square root of 36 is 6. Therefore, the square root of 29 should be somewhere between 5 and 6. All right? So my first bounds on it are 5 and 6. And so my first guess for the square root of 29 is the average of these two numbers, one of which is too small and one of which is too large. So the average is 5 plus 6 over 2, and that is 5.5. Okay, having taken that guess, I reason as follows. If the square root of 29 were really 5.5, then if I divide 5.5 into 29, I would get exactly 5.5 as the answer, right? Two equal factors that give you 29. So I try it. I divide 5.5 into 29. And of course it's not going to go in equally because I'm never going to be that lucky to guess right. And when I do the division, of course I'm not going to do it for you here. I did it already. I get 5.27. Now notice what I did was I carried the division out one more decimal place than the number that I started with. I started with one decimal place, 5.5. I carried my division to two decimal places, so I have 5.27. And now I take as my second guess, I take the average of 5.5 and 5.27. Why? Well, because 5.5 is really too large. I know it's too large because when I divided into 29, I got a number that was smaller than 5.5. And 5.27 is too small. Now, I could check that on a calculator. If I square 5.5, I'll get a number that's bigger than 29. If I square 5.27, I'll get a number that's smaller than 29. So my second guess is the average of 5.5 and 5.27. So that's 5.5 plus 5.27 divided by 2. Now that works out to be 5.385. But you see, I really shouldn't carry it out to three decimal places because I've only started with two decimal place numbers. So I'm going to round this back to 5.39 as my next guess. Actually, of course, if I look back at what I know the answer was, I probably should have stuck with my 5.385. But really, the right thing to do is to be no more accurate than the original numbers were. So I have 5.39. And now, what do? Well, I repeat the procedure. Now I take the 5.39 and I divide it into 29. And I go as many decimal places as I had plus one more. So I take 5.39 and I divide that into 29. And when I do that, I get 5.380 for some reason to three places. And so my next guess, my third guess, is the average of these two numbers. And that's 5.39 plus 5.380 divided by 2. And that's 5.385. OK. I could keep doing this as long as I want, but I'm not going to. I'm really going to stop because nobody's going to expect me to figure this out to hundreds and hundreds of decimal places. What I'm going to do is take a look. My first guess is 5.5. So first guess is 5.5. Second guess is 5.39, which means if somebody said to me, get the right answer to the nearest tenth, I would calculate it out to the nearest hundredth, 5.39, and round off to the nearest tenth. So to the nearest tenth, I would say 5.4. Problem 12. Find the square root of 9x squared. All right, one little comment here that I must make. You remember when we took the square root of minus 7 squared, we got as a result 7. But I'd like to be able to say that the square root of x squared is x. Now, if x is a negative number, that's not going to work out correctly. As you can remember, again, minus 7 squared, if you take the square root, you don't get minus 7, you get plus 7. So it's been an understanding in algebra courses for years that when we have square roots and we have variables underneath those roots, under the radicals, it's understood that the variable represents a positive number. Then we are safe in saying that the square root of x squared is x. Well, what about the square root of 9x squared? Of course, you have to ask yourself, what do you have to square? What do you have to multiply by itself so that the result is 9x squared? And that's easy. That's 3x, because 3 times 3 is 9, and x times x is x squared. Of course, you can check this, right? This is 3x squared gives you 3 squared is 9, x squared is x squared. So you see the square root of 9x squared is equal to 3x, because 3x, the quantity squared, is in fact 9x squared. In number 13, we have the square root of c squared d squared. And again, ask yourself, what must be multiplied by itself so that the result is c squared d squared? Well, to get c squared, of course, you have to multiply c times c. And to get d squared, you must multiply d times d. So therefore, to get c squared d squared, you must have cd times itself. cd times cd is c squared d squared. Problem 14, we have a product of 3 things under the radical. We have the square root of 196x squared y to the 4th. Once again, ask yourself, what do I have to multiply by itself so that the result is 196x squared y to the 4th? Well, remember I told you should memorize some of those perfect squares, and here's one you should have memorized. 196 is, in fact, 14 times 14. So the square root of this is going to be 14 times. Now, to get x squared, you must have had a factor x. And to get y to the 4th, well, what's y to the 4th? It's y squared times y squared. So this is 14xy squared. Square root of 196x squared y to the 4th is 14xy squared. Problem 15, we have the square root of 0.49 a to the 6th b to the 12th. Same reasoning. To get 0.49, you must have had to square 0.7. To get a to the 6th, you have to square a cubed. Is that right? A to the 3rd times a to the 3rd is a to the 6th. And to get b to the 12th, you must have had b to the 6th times b to the 6th. So the square root of 0.49 a to the 6th b to the 12th is 0.7 times a cubed b to the 6th. In this section, we're going to simplify some radicals by using the rule the square root of ab is equal to the square root of a times the square root of b. Now, the way we can use this to simplify the radical is to take advantage of any perfect square that we can factor from the number under the radical sign, from the radicand. Take example 1. We have the square root of 12. 12 can be factored into, well, 2 times 6 or 3 times 4. And what we want to look for is a factorization in which one of the factors is itself a perfect square. In this case, that would be 4. So we want to factor 12 as 4 times 3. And we're going to write this with the perfect square first. So this is 4 times 3. Now we use the rule that says the square root of a times b is the square root of a times the square root of b. So that's the square root of 4 times the square root of 3. The square root of 4, you see, we know because 4 is a perfect square. So the square root of 4 is 2. So this is 2 times the square root of 3. Notice, this is multiplication. The two things are next to one another. It's understood that's 2 times the square root of 3. Now, of course, in the previous set of problems, we had a square root of 29. that we worked out to the nearest tenth. But in most cases in mathematics, we leave answers in radical form as long as we've simplified the radical down in this way so that what's left underneath the square root sign can not be made any simpler. And of course, this is really the right answer because this is exactly the right answer. This is 2 times the square root of 3. If we tried to work it out to the nearest tenth, that would really only be an approximation. Let's take a look at number 2. We have the square root of 50. Once again, we ask for factors of 50 such that one of the factors is a perfect square. Well, 50 could be 5 times 10, but if you want to get a perfect square, what you really want to write is the square root of 25 times 2. All right? Now, if I factor this, I have the square root of 25 times the square root of 2. And the square root of 25 is one I know. That's why I did it this way. And I get 5 times the square root of 2. Number 3, we have the square root of 63. Once again, how can I factor 63 so that one of the factors is a perfect square? The answer is what? 63 is 9 times 7. The square root of 9 is 3. I think I'll write it this way again. The square root of 9 times the square root of 7. The square root of 9 is 3. So I have 3 times the square root of 7. Problem 4, we have the square root of 80. Now, here's something you should look for. 80 can be factored in many ways. The first thing that I see that looks easy is 80 could be written as 4 times 20. All right, 4 times 20, that's the square root of 4 times the square root of 20. The square root of 4 I know is 2. So I have 2 times the square root of 20. But you see, now I'm not done, because 20 itself can be factored into 2 factors, one of which is a perfect square. I can write 20 as 4 times 5. So this is 2 times the square root of 4 times the square root of 5. Square root of 4 is 2, so this is 2 times the square root of 5. In other words, it's 4 times the square root of 5. But you see, I went through a lot of steps here, and I could have done this more quickly if I had been careful to do the factorization so that I factored the largest perfect square that I can find. You see, I could have written 80 as 16 times 5. Now, 16 is a perfect square, and it's much larger than 4. All right? And now I write this as the square root of 16 times the square root of 5. The square root of 16 is 4, so I have 4 times the square root of 5. Of course, it's the same answer, but I did it more quickly. Now, there's 2 lessons here. Number 1, if you want to do it quickly, look for the largest perfect square. But if by chance you don't see the largest perfect square, you can still recover. That is, you can always go through it and go one more time, look for more perfect squares. So you can whip the problem 2 ways. If you're quick, you'll find the quick way.